Hello everybody. Welcome to today's session about attention mechanism. It's a very important milestone in the sequence and sequence modeling. From our earlier encoder to decoder network architecture, we could correlate that there was a problem. And when we implement attention, then some of the problems are going to be solved. In attention mechanism, the model focuses on certain important parts of the long sequence and thereby overcoming limitations of the network, which otherwise cannot remember a long sequence. And you will appreciate that in the biological attention point of view also, we humans don't really focus on the entire sentence when we hear them, or when you watch a long video. We focus on certain frames or certain words more than others, given the interest what we have, and then we pick up those points and the words. So in a similar manner attention will work. Now let's jump into the mathematics of attention, and then from there we'll go to the implementation through code. This is where our last presentation ended, where we have the encoder and the decoder. The input and the outputs are presented in a horizontal manner. If we focus on the decoder part, the left side of it, y1, y2 and yt dash were coming from the left of the decoder, and the y hat 1 to y hat t dash were going out from the decoder as the output on the right side of the decoder. In this presentation, we are going to stay with the same architecture. There are three changes which are there. The changes is that first, the decoder is rotated minus 90 degree. As a result, the y1, y2, yt input to the decoder are coming from bottom, and the outputs are coming out from the top of the decoder. So that's change number one. Change number two is that we are representing the hidden state of the decoder by S. S1, S2, do you follow? Earlier it was H. So now this is S. Encoder still remain H. Third change is the decoder's time steps, which are 76, if you remember from the code. They are represented as I. Si will represent ith time step of the decoder, and for the encoder it is J. Now with all these three changes, let us now remember what was the problem we spoke about. We spoke about a summary representation of the entire sequence which was given to encoder, because the source language and the target language will have different number of words. As a result, we had to take this method of summarizing the source language and then give it to the decoder. And then we ran into some problem. So let's recap the problem. What was it? As the words were coming in the decoder, the context was C, first time step. When we move to the second time step, still the context remain at C, and so is for the last time step. So the context are not changing, and that is leading to couple of problems. Number one problem was that we were discarding all the encoder's output. Although encoder was capable of giving you one hidden representation for each word at each time step, we discarded all of them and took the summary. The second problem was that the size of the vector or the size of this hidden representation could be also a problem, because if it is not adequately sized, it will not capture all the necessary information from the sequence, which is very difficult to guess what size would be appropriate for capturing all the sequence. And if the sequence is really large, it will be practically impossible to capture make the size that large of the hidden vector. Third is that it was static. It is a fixed context vector which was not changing as the new words were appearing at the decoder time step, right? So now how do you think we can solve this problem? Well, one of the way we can solve this problem is to take all the input from the encoder and then make an average from this input and then feed it as a context. With that, we will be able to solve the first problem, that we were discarding the time step from encoder is now addressed. However, the remaining two remains. What if we, instead of average, we take a weighted average? And you know that basic common sense is leading to this path breaking concept of attention in the RNN or in the sequence modeling. So what we can see is that our objective here is that can we somehow utilize the states which are coming from decoder as a mechanism for weighting the words in the source language, which is the hidden output, which means that we wanted to utilize the S0 to weight the H or the H1 to HT. What it means is that how well S0 matches with one of this time step HJ. Taking our example of Hindi to English translation, if we are at the target language and we are speaking that I like and we want to focus on the word like, so the like goes here, and then on the source language which is Hindi, where we have spoke about that mujhe machine learning bahut pasand hai, so many words, so he is asking my second word which is like matches with which of your word. So it is pasand, which is probably fourth or fifth word in the Hindi sentence. And that's what is the attention, that it is a function of both this hidden state. Very simple, isn't it? Now, what do we do? By using this function, we get the weight, which is alpha, named as alpha. It is for the S0 word, S0 hidden state, and then that alpha 0, so therefore it is represented alpha 0 in all time step. Alpha 0 is used to multiply the words, each of this word, mujhe machine learning bahut pasand hai, each of this word will be multiplied with this word to identify which one is of more important. Very nice concept and easy concept to understand, right? And profound impact that we will see in our code. When all this weighting is done, they are summed up, this plus signs, and then the first context vector is generated, C1. But we don't stop here. When the next time step appears, in fact before next time step, you know, when the C1 plus Y1 is given to the decoder, the result will be S1. So Y1 is conditioned on the C1 to give you S1, and the next word appears. We utilize now S1 to recalculate the context C2 in a similar manner. We convert S1 as a weight. That weight we multiply with each of this word or the hidden representation of the word coming out from the encoder, then sum them up to create this C2, and the process goes on till the T dash time step. When we take T dash minus 1, just the step before, that hidden representation is used to calculate the context for that step. We are following here that at ith step, we are using the I minus 1, like here. At T dash step, we are using T dash minus 1 state from the decoder to calculate the weight. The only thing remaining to be understood is what is this function? How exactly we are calculating this alpha, right? Let's move to the next part. Well, with that, as we can understand, all the three problems which we mentioned are addressed here, because the context is now changing over time. Its size is not fixed. It is also aligned because now the input and output are actually aligned. With every time step change in the decoder input, they are getting aligned by this weight. Well, objective over here is to convert the states to weight. You take any of the state, S0 or S1, we'll take S1 right now, and then our objective is to convert it to weight. In order to do so, the first thing we do is broadcast S1, repeat S1 that many times, as many as the sequence number which is there in the encoder output. So 1 to T is the encoder output, and since we have to do some operation on them using this S, we are first repeating S. This is what is called the broadcasting. In NumPy array operation or tensor operation, we normally broadcast this when between the two arrays or two tensor we find that there are some differences. So to make the operation successful, we'll expand one of the dimension. That's what is the broadcast. Okay, we'll show that in the code, by the way. Now this is passed through a neural network, which is called the dense neural network. Network number 1 for attention calculation. This is additional neural network which we are introducing. Once this is passed there by, and if they are the weight and biases, you can see they are in dimension, capital N dimension. Remember, this is what will be the attention layers number of neuron, capital N. We can consider these are our rows 1 to T, and we have this presented here are also rows, but we will transpose them so that the matrix calculation can happen. So the neuron equation is also WT, which is weight transpose X, which is the input, plus B, right? So yes, this is what we will transpose. Therefore we will have T number of rows and N number of columns giving you this matrix. T rows, N columns, T by row, column. And this is what we are calling as a Q matrix, is what is learned now. Q stands for query. By intuition you can think of query like I have given that word like, quote unquote like. So if like is the query, I want to go to encoder and who has got 101 sequences, words, and consider that as a database. So the query is sent there to ask, hey, which word closely matches with like? So like is the query, and the answer coming from the encoder are the keys and the values. Now how do we create those keys? Is through this layer. So all the hidden state are now passed, of the encoder is passed through this dense layer, K1 to Kn, in matching with the same attention units, resulting you a K matrix or the key matrix, which is T by N. Now we have the query and the keys. We will do the operation on them so that it can be converted into a common score. And there are several ways this can be achieved. The first one which was proposed is a additive attention, proposed by Badnau in 2015 through his paper Natural Machine Translation by Jointly Learning to Align and Translate. So this was a paper in 2015. By the way, 2014 is the time when Badnau was the second author of the another paper, 2014, where he proposed this very RNN encoder-decoder concept for machine learning concept only. That's another paper, and this is the second paper. Okay, within 1 year this improvement was proposed by the same author. Okay, now we have to convert this to a score, and how it is, it will be passed through another neural network. So far we are speaking about network number 1 query, network number 2 keys, and network number 3 for converting into score. Score is nothing but another neural network whose output is only one neuron, so that what comes out from there is a scalar, and that can be seen from this equation, which is in dimensional vector is now converted into a scalar 1. So there are T number of score. One score for each of these time step is calculated through this coding network. The score is also called the energy score. That's how it is E, and it's a function, attention function, therefore it is A. So EIJ is attention of the decoder's state and the encoder state. Very simple, right? The score has come. One more thing can be said about the score is that it's akin to a regression problem where you have given x1 to x2 variable, which are our in variables, and then at the very end you are trying to see what is the regression score or regression number that the model can output. So very similar to that kind of network where scoring is doing. Now you are converting the score to weight through softmax function, which is scored by the summation of all other score, which will give you a ratio which you can tell it as a probability or a weight with respect to all other. Fine. Often in the literature you will see that this concept and that these operations are presented in a pictorial format like this, which is a table where we are talking about the columns are the HTs, the steps, and the states are here. So if we are interested in the S0, we basically apply S0 on all H1, S0 H1, S0 H2, S0 HT to get the score, which is now converted to weight alpha 0, 1, 2 and so forth. And when we are talking about the weight is nothing but the one value divided by the summation of all the value. It is easy to understand from this table, right? This was the question which we wanted to understand, that how a state is converted to a score. We understood that basically we introduced three number of neural network. One is for Q, one is for K, and another is for scoring. These three neural network will be used to calculate this weight from the state, converting state to the weight. And the mathematical formulas are basically this one, which is Eij is equal to a attention function of, or A is also sometimes called the alignment function. A stands for attention, or it could be also alignment, because it aligns the input and output outwards, right? Equation for context is easy to understand. We basically apply or multiply the weight with the hidden state, which we had done in our previous animation slide. And for example, if we are interested in C1 to calculate the context 1 at time step 1, we'll be using I minus 1, which is S0, and then their weight will be multiplied with H1. So alpha 0, 1 multiplied by H1 plus alpha 0, 2 multiplied by H2 and so on. That will give you the C1. Now, the C1 will be added, concatenated with the Y1. Okay, this concatenation in the original paper you will see is actually presented here. It is concatenated along with this one. I could not find the exact code which implements this paper. Maybe it is there, I didn't do search properly, but I coded on my own, and in my implementation I have done that just to prove the point that how attention is effective. So this also worked, okay, in my implementation. Okay, now similarly the C1 will be added at time step 1, so therefore on the other time step this will be added. But this addition, this concatenation will change the shape of the original Y1. Therefore, we will introduce another neural network which will convert this concatenation into a learned representation of the input, and which will also match the dimension which is expected by the decoder. So we are speaking about 1, 2, 3, 4 network. So first we'll show you through the code this 3 network, and then the last one will also come into picture. Remember all these 4 which will be required during the coding part of it. Okay, now all done, we are moving up to the code now. Main point, where we are initializing variables similar to what we did for the in the last presentation. The changes are here that we introduce the attention units as 64. What is attention unit? The capital N, remember that. Attention units are the capital N, right? We showed you there. You want to go there, see. You look at this N dimension, this N dimension, this N dimension. All of them are basically the attention units. Back to code. Okay. And we change the RNN units, which we explained in the last video, from 512 to 256. And because of this change, I would like to show you that I have run this with the new data 256. So this entire encoder-decoder I have retrained, and the score now is 7595. Along with this, there is another change which I have introduced, is that I introduce AUC, area under the curve, one of the metric which will be used to, it actually better measure the categorical cross entropy, multi-class classification. Accuracy is not a very good metric there. So I introduce AUC to show you the impact of attention there. And let's now just observe that after 15th epoch, it has achieved 77.42 as this AUC score. Okay, now time has come to the core subject. How do you implement a attention layer particularly the additive attention proposed by Bajnau. We spoke about three networks, if you recollect: Q, K, and this core network, and they are initialized by attention unit, which is 64 in dimension, each one of them, Q and K, but the S is 1 because it is finally giving you one scalar number. So QKS is initialized. The next we said that the state vector has to be expanded, or it has to be broadcasted, matching with the time dimension of encoder. See this code. tf.expandDim does that exact job. Okay, what it does, let me show you. So this is the query. One vector of 256 elements has come in. When we do the expand, it adds one more dimension here, which is 1, but this one, whenever it is performed with performed operation, either summation or multiplication, for example k is 101, this will also expand to 101 times, repetition will happen, and then summation will be possible. Okay. So q plus k is the q plus k of these two, and then they are passed through a tan-H activation layer. The resulting q plus k is 101 number of learned vector, which has 10 elements within that. And then this coding function, which is pass it through another layer, the third network. Here it is. We are passing it through the self s dot s, which is this code network, and then pass this q plus k inside this. This will give you the scalar number. Here it is. It has given you the scalar number, one of them. And then the scalar number has to be converted into attention weights, right? That is where we are performing the softmax operation, where score has been given. So yes, this will be also one dimension. Now the weight will be used to multiply each of the time step, which are the values. At this stage, you have the score. Now you are going to multiply them. You are going to multiply only, and summation will be done at the next step. Here it is. We are multiplying them. The star is the multiplication from the context vector, and the context vector is actually the sum of all of them. So alpha 01 multiplied by h1, alpha 02 multiplied by all the way to up to ht. So this is where you are doing the summation of all of them, the multiplied result, which will finally give you the context vector. Fair enough. So basically this is how it will be called, attention layer. Then you give the state and all the output of the encoder, all the time steps, which are the values. So the state and the values given, it will give you the context vector. Come here now is about applying this attention layer inside our decoder. Encoder remains same, nothing to observe, same thing which we had done before. Return sequence on, return state on. Decoder is what is interesting now. In the decoder we are incorporating the attention layer, and decoder input, you remember, that had to be transformed because there is a concatenation happening between the input and the context vector. So we want to transfer them by the one tan-H activation and a dense layer having RNN units. This RNN units will again transfer it to the required hidden state expected by the decoder. Attention layer is initiated, and then the decoder output was also having the dense layer so that it matches with the actual word size, which is just similar to previous encoder-decoder architecture. Here is something new. We are introducing all outputs as the array. And why you are doing so? Because this is the place where all the output will be stored. Let me explain it from the PPT once again. Now imagine that these input are now coming one step at a time. At the end, we are getting only one output because the output return sequence is false. So we are not getting all the output at time step 1, only one output. That we store it into that all output array. Similarly, for each of these time step, we'll be collecting the output into that array. Then finally at the end of iteration of 101 time step, we'll create the all output as if the return sequence has been given. Okay, so all output is that array purpose. Input is the decoder's first word, taken here 0th. State is the first state is 0, where the feeding is done from the encoder state, which is last hidden state. Very similar to our encoder-decoder architecture. Only these two are new introduction. Okay, now we are iterating through 101 step, I ranging for I in range of decoder sequence length, passing the state and all the encoder output to the attention layer. S0 has gone now, and all the 101 words has been also given as value. So this is your query, this is your value. You got the context which has to be concatenated. You do the concatenation this way. tf.keras.layer has a concatenate function where you are giving the input and the context vector. It will return you the decoder data plus context. As we said that has to be transformed. So these two lines will do the transformation. Passing it to the 1, 2, 3, 4th network layer, decoder input will be going to that dense layer. Then finally shape adjustment will be done, and you get the data ready, concatenated data ready to feed into the decoder. So that's the additional step which you are doing. And then you pass that data to decoder actually, which will give you state S1. We fed in S0, now we are getting S1, and output is y hat 1, only one output. That output is passed through the decoder dense layer to convert it as a word and softmax and all those collected in the all output, which we just explained. Next step, now input is changed. It is now changed from 0 to 1, and the state has changed from S0 to S1. With this new 2 input query and the new input which is y2, with these two values, now we are going to recalculate everything. State is changed, which is S1 now, and the input is changed, which is y2 now. And then we are collecting this output as a tensor, because we are in the TensorFlow, we cannot match a normal Python list, so that has to be converted to a tensor. That's what we are doing here. Then finally we are building the model with and then training, just like the same as vanilla encoder-decoder. New metric introduced as AUC, every other things remaining same, 15 as the epochs. We adjusted the batch size little bit here because there are multiple layers of neuron now. Apart from the encoder and decoder, we introduced 4 more layers. So we will require little hyperparameter adjustment, which you have done here. And in both places, encoder and decoder, we have also introduced a little bit of dropout here. Okay, look at this now. This is what will inspire you of all this hard work which you have done so far. You see the improvement here. Earlier it was something around 77% of changes. Now it has jumped up to 15% because of the introduction of attention. 15% changes. That's a noticeable change when you are dealing with a sequence-to-sequence network. Accuracy have also changed a bit, but as we said, it's not a very good measure. Let's focus on the AUC, 92.29%. Okay, and that too, not introducing embedding layer, we stayed with one hot encoding of each of the word, which is said that only one representing the index number for the word out of 3000 or 4000 elements, and remaining all of them are actually zeros, is a very inefficient way of handling word representation. That's not how it will be done. In the subsequent video, we'll get into all this complexity. It will be learned, the word will be run through embedded representation. But at this time, we wanted to focus only on simple RNN and the attention. Finally, you might be wondering that why this for loop? This helps us to understand very clearly what exactly is happening. But in reality, what will happen, we'll take help of cells of Keras RNNCell, which is a lower level unit. Normally that simple RNN takes care of the iteration as well. But when you go to RNNCell, then that is a one single time step. So this by subclassing a layer and then creating a state, we could achieve the same thing. You see, we are collecting the state from the, and then we are collecting the outputs here. Context vector is calling the attention layer, then concatenating, then that concatenated vector is passed through the RNN decoded cell, and the output is obtained. Very similar to what we had achieved earlier. And then every other things we are right now, you can see this cell is now finally used in layers of RNN, which is a higher level cell which does that iteration part much more efficiently than the way a Python for loop we have written. We'll achieve very similar result. That was 92%, this is 91%. That's all about our discussion or our presentation about the mathematical formulation of the attention layer and exactly what is happening inside. We also implemented through code, and we got our reward by seeing that there is a 15% improvement when you introduce attention into a vanilla simple RNN. Okay. Well, just to summarize what we have learned so far, we started with the encoder-decoder problem of a fixed context length. Then we spoke about a basic concept of utilizing all the time step from the encoder and creating an average out of this, but that wouldn't solve the context changing over time step. That is how we introduced a weighted average, which is an improvement on the normal averaging, and also we made it changed by the weight was changing per time step or per word of the target sentence. Now the question was that how do you get that weight per time step? So we utilize the state vector of decoder as query, and those queries were converted to a weight, and these queries were going to the encoder as if the encoder is a database which has got key and value store which will address to my query. So introduce this concept of generalized attention of Q, K and V, query, key and value. Then we moved on and showed exactly how these calculations are done. Basically, the query and the key are first passed through a dense layer of R T into N, T by N matrix. Then they are summed up. This summation could have a different shape of operation which we learn in subsequent videos. Then those summed up matrix was passed through a neural network to convert it to score, and the score to weight by a softmax. Once we get the weight, we know that how to apply the weight to the time step and get a context which is also changing as the decoder input changes. We are now ready and we have achieved a big milestone which will help us to learn the future concept and finally will lead to LLM. And when we reach to there, you will see that layers and layers of concepts are building up, but we will be very strong. We'll catch them very fast because our foundation buildings are also becoming very strong. Okay, see you then in the next video.